All right, good morning, class. Today we are going to move on to our last set of energy wave notes. So these are discussing the last two of the four wave interactions. In the previous notes, we talked about reflection and refraction. So in these, we'll be talking about diffraction and interference. Diffraction is the bending of an energy wave around a barrier or when it moves through an opening in a barrier. And in this drawing down here, sometimes reflection and refraction are easier to understand because we see those on a more common basis, and they might make a little bit more sense because of our background knowledge. Diffraction is something that might be a little bit newer knowledge. So if you look at this diagram down here at the bottom of your screen, it's showing water, and water is a medium that often we can view diffraction in. So here you have the water that's moving in between two areas that it cannot pass. So this is a medium, a barrier medium, so it cannot pass through this area. So, but there is an opening in this area in which the water can pass through. So when it is able to pass through it, what happens is when it gets through it and there is a larger area of water on the other side, it bends and slightly changes its direction. Okay, so this also applying to sound is one reason why, if you think about it in the hallways, if you're walking down one hallway and you observe your friend walking down another hallway, and you observe them first by hearing them. So if you're on a corner, friends walking this way, you're walking this way, you can't really see them yet, but you can hear them. And the reason why is because as that sound wave hits an area where you have it has to bend around the corner, it's going to spread out, and so you'll get that spreading and bending of sound. You'll hear your friend before you might even see them. I'm going to go ahead and click on this link and we'll see where it takes us. And it's saying that it's not found, so we're going to go ahead and X out of this and head back to the PowerPoint. Alright, so a couple things that you need to know about diffraction is that the gap that is in between the barrier medium that the sound waves are able to move through will affect the amount of bending and spreading out of the wave. So here we have the same wavelength. So here is, you can see that the distance between the particles is even, so we to this over here. And so we have like an equal wavelength in both of these diagrams. However, the difference is this opening size in the medium. When there is a larger gap, there is less bending of the sound waves. So you can see over here that there's not a lot of bending of these sound waves, and there's not a ton of spreading out. It's still a pretty narrow funneling of the energy wave. However, on this side, when we have a smaller gap, it causes to bend, and you can tell that the waves are spreading out over a further distance and they are bending more. So down here, the wavelength is a little bit larger, so it's a little different than the ones up top on this diagram, but the gap is still, sorry about that. The gap is still smaller, and so we have much spreading out and much bending. If we were to close this gap even more, if I were to close this gap, you would get even more spreading out and even more bending. And lastly, if we are to back these, make the gap larger between so if we widen this gap right here and spread this medium out further, then you would get less bending and less spreading out of sound waves. And so it might look more like this, where you don't have as much spreading out. So those are just some different ways to think about diffraction. Here, this is more like an optical illusion right here. You have energy waves moving. Here is a double opening in a barrier medium. So you get this diffraction here. You can see in this diagram where it is causing the energy waves to spread out, and because it is a rather small opening, they are spreading out quite a lot in that. Next, we're going to look at interference. There are two types of interference: destructive and constructive interference. And I would recommend that you go onto the PowerPoint and you look at this YouTube video. It does show a good example of interference, and I'll let you do that kind of on your own time as a review. But with destructive interference, this bottom diagram kind of shows you this. And the one thing I don't like about this diagram, and you might want to add this to your notes, is that it really needs to have a rest line. So this is where the medium would be if there were no energy waves moving through it. But since there is an energy wave moving through it, the medium can be disturbed up to the area of the crest or down to the area of the trough. And if these waves were coming towards each other, so if this one was moving this way and this one was moving this way, and they were to overlap, what would happen is this crest would meet up with this trough. And so now we kind of get into talking about positive and negative amplitude. So here, because this is a positive amplitude, meaning the medium gets shifted upward in this diagram, and in this energy wave, the medium is getting shifted downward. And if these cross at the same time, then you're going to get, if we were to put numbers, you would say like a +2 amplitude, and then here would be a -2 amplitude, since these are identical waves just moving in different directions. And so when they cross, what would happen is that you get a 0 amplitude. So the medium actually at that second in time would just go back to being undisturbed. So basically, this is the key right here, that during destructive interference, you would get a smaller amplitude. It doesn't have to end up being 0. It just might if you have two identical waves moving towards each other. Other than that, we're going to look at constructive interference, and this is the opposite. This is where you'll get a higher amplitude, larger amplitude than if you just simply looked at each wave. So if we say the amplitude here is a +2 because it's going from the rest to the crest, and this is also a +2. So when these cross, this one's going this way and this one's going this way, and they cross, these two amplitudes meet up, and what happens is in this one we get a total amplitude of 4. All I did was add these two together and I get 4. Now it's not always going to double like that. Remember, these are two identical waves, so that's why we just double the amplitude. The main thing is that with constructive amplitude, you're going to end up, when those two waves interfere with each other, you're going to end up with a larger amplitude. Now last, we're going to get into standing waves, which I really love to talk about. We have some cool demonstrations that we're going to do tomorrow during class, and that would be on Friday. Depending on when you're taking these notes, we'll do them in class on Friday. So this is about standing waves. Standing waves are basically, and this goes back to reflection, so this is going to kind of test your knowledge again and review your knowledge on reflection. Remember that a reflected wave bounces off a barrier medium. And when we studied it, we always talk about the incident wave coming in at an angle and then it bouncing off at the same angle. I may not draw this the best, but that the incident angle and the reflective angle are equal. And so we have here a standing wave. The only difference is that if this is your barrier medium and this is then your normal line, you have a wave coming in on the normal, so at that 90-degree mark, and then what happens is it bounces off and it comes right back on itself. So the same energy wave is interfering with itself. That is what a standing wave is. So this diagram what's happening is you have, let's say, a barrier medium here. The energy wave starts moving in this direction, and so you've got a trough and then a crest. Oh, it bounces off the barrier medium and it comes right back on. So you've got this energy wave that's going in this direction, but then it is also bouncing back in this direction. Okay, so just kind of review that, and here is just a longer picture of it. Same thing, you have a barrier medium, you have this wave coming in, here's the rest line, and then you have, it hits this barrier medium and it comes back, and so you have equal amplitude that it was traveling with before, just on the opposite side of the rest line. Now you can see here that I have a link, so you might want to go back and check this link out and see if that helps you review the information. Last thing we're going to talk about is resonance frequency. Frequency, just to remind you, is the number of wavelengths per second of time, especially if you're measuring in hertz. So the frequency, resonance frequency, is the frequency that causes a standing wave in a medium. Believe it or not, lots of things vibrate naturally, and so they kind of have a natural occurring frequency, and that is the resonance frequency. And so if something near an object starts to vibrate and those waves go towards that object and it matches the object's natural frequency, this object will start to vibrate, and it will continue to vibrate until something stops it, basically. So when a different object over here starts to vibrate due to some force, and it happens to match up with another object's natural frequency, it will cause the object to start to vibrate at that natural frequency, and it will continue to do that for some time. And here I have something that you might want to watch. I think this is a Mythbusters type short video about resonance frequency with some glasses, so you can check that out. Lastly, a real life event that occurred is Tacoma Narrows Bridge. You can go on the PowerPoint and click on this video. It's kind of a dry video, however, it's kind of interesting. It'll take you about 5 minutes to watch, but it is a great example of this. The wind started to blow. This building was, or this bridge was built, was utilized for a very short time, and when the wind started to blow very strong one day, it matched the resonance frequency. So what happens is you actually see this bridge, and you can see it kind of having a standing wave occur on the bridge. So the bridge kind of does this teeter-totter motion back and forth, and eventually the bridge cannot take the stress of the movement that's happening due to the natural frequency being matched by the wind, and so it collapses. And there's a short story of a dog that was stuck in a car on the bridge, and so if you want to know the ending to that story, you can watch the video. I hope this all makes sense. If you have any questions, please make sure that when you come up and see me during checkpoints, that you ask any questions that you have. So star your notes, make sure you added things to your diagram. When we go over demos, add information in to help you when you're studying. Thanks.